What's up, guys? It's your favorite physics LARPer, apparently. That's what everybody thinks. Today we're going to be motivating the Dirac equation. And this equation is the foundation pretty much for quantum field theory. Now, we're making this choice of motivating special relativity first. So let's go ahead and do that. The relativistic mass shell. What this is we can first consider a particle of rest mass m moving with velocity v in some inertial frame. So we can just say that the correction for E equals mc squared for p is equal to gamma mv squared, where that's the momentum. This gamma here is the Lorentz factor. Hopefully you've seen it before. I'm assuming you've seen it before. And what it does is it assumes that, again, you have a mass moving with some velocity in this new inertial frame. What you can do is square both of these quantities and define something called the dispersion relation, m squared c to the fourth minus gamma squared m squared v squared c squared, which should be equivalent to gamma squared m squared c squared minus v squared, which should give you m squared c to the fourth. Okay. The relation, or the dispersion relation between energy and momentum that we are able to get independent of the observer's velocity is just moving this term over to this side here. I'm not going to go through like the full algebra, but you should be able to compute that and verify that for yourself. P squared c squared plus m squared c squared to the fourth. All right. It's independent of the observer's velocity, but we have the momentum, right? We still have that momentum quantity. So why this is important in special relativity is what we'll do is we can define something called a 4 momentum, and where mu is just the index between like 0, 1, 2, 3, where 0 is time and 3 is the space dimensions, so it's like 1 plus 3 dimensions. Mu, or p mu, is equivalent to E over c in the time component and then momentum in the space component. So momentum x, momentum y, momentum z, right? So this would be more like a bold p for the vector. And it has something called, inscribed with it, it has something called a Minkowski metric. So it looks like eta mu nu commonly. And this is just a diagonal matrix that runs from 0 or 1 and then minus 1s like this. So it'll just be like 1, negative 1, negative 1, negative 1. Okay? So positive for the time component, negative for the space component. But we can adopt this sign convention. So the invariant is going to be the contraction of these two indices here. They give us e squared c squared minus p squared, p is momentum vector, is equal to m squared c squared. And all observers are going to live on the value of this Lorentz scalar. Okay? And so from this 4 momentum, we're able to use the relativistic dispersion relation that we derived previously. So what this means is, because all of the observers are agreeing on this value of this Lorentz invariant scalar quantity, after contracting our 4 momentums, the particle is going to live on something called the mass shell hyperboloid. And you can look up a picture of this. basically allows us to define the difference between virtual particles and actual particles. Okay? And any relativistic or any viable relativistic quantum field theory preserves this invariant. So the energy and the momentum operators can be combined into a single 4-vector whose square yields the same constant here. Now that we have this tool from special relativity, we can now construct a, or we can now justify something called the Lorentz group. And why quantum theory and representation theory, the representations of groups, why these things are all kind of packed together and why I'm exposing them in this mathematical way. So the Lorentz group, or specifically the orthochronous Lorentz group, mathematically is not simply connected, and its double cover is SL2, C. And this double cover acts on two component objects called spinors. We have seen them before in the previous episodes, but we're going to really kind of show why the fundamental representation of SL2, C carries the full topology of the Lorentz group, okay? So, and why spinors are these primal type of objects before vectors. Spinor fields become these fermionic type of fields. So, and this comes straight from relativity, right? From relativity. So, we can encode any space-time vector. Okay, so let's say a space-time vector x mu as a 2x2 Hermitian matrix. Okay? By doing this, where we have our Pauli matrices, except we can define the 0th Pauli matrix as just the identity 2x2 matrix. So just 1, 1, like that. Okay? Now, what's interesting about this, because as you recall, when we had Pauli matrices in quantum theory, and of course, we're using the same Pauli matrices here. Okay? As you recall, there are these types of objects that allow us to describe quantum states. But if we take this x and we where x1 or x0 is time, the time variable, x1 minus I x2, x1 plus I x2, as you can see, it is Hermitian. That means it's invariant if I take the transpose and then complex conjugate the matrix. Okay. Now, if we choose to compute this determinant, the determinant of x here, that should give us x0 plus x3, x0 minus x3, minus x1 minus I x2, x1 plus I x2. And if we were to FOIL these guys out, x1 squared minus x2 squared minus x3 squared. So thus you would then have that the determinant itself of this matrix X that was encoded by the Pauli matrices, we would have that it's also must be a contraction that evaluates to a scalar quantity, because it was the determinant of this of these Pauli matrices here, and this determinant also just happens to be the Minkowski interval. So all right. Now what we can do is we can consider a transformation on this matrix itself. So let's say we have x going to x prime. The transformation would be related by x a acting on x acting on a dagger, where a belongs to the special linear group SL2 comma C, where the determinants of A are equivalent to 1, such that. Okay, that's what a special linear group is. Okay, versus just a general linear group. All right. So without having to compute anything, we can say, well, the determinant of x prime should give us the determinant of A times the determinant of x times the determinant of a dagger, which should give us the determinant of x. Thus, we have the invariance. This induced transformation on x mu here, it preserves Minkowski length. All right? It's a Lorentz transformation, ultimately. So what we've shown here mathematically, and what makes a lot more sense to think about, is that the orthochronous, or the proper orthochronous Lorentz transformation can be represented this way, and the map from A mapping to some lambda, to some lambda representation of A, is a 2 to 1 homomorphism from SL to C onto SL1 comma 3. And these objects directly, they transform directly under A, and the objects themselves that directly transform under A are what are called left-handed spinors. Spinors. So we have a left-handed spinor here that transforms under A. And what we can do is similarly define right-handed spinors. Transforming under a dagger, the inverse of a dagger. Okay, so the idea is that these spinors arise because of the symmetry group of space-time, and they have a deeper covering group with representations that are more fundamental than vectors and tensors. Okay, so let's look at what spinors actually do. Just we're being kind of axiomatic about the SL. We don't want to go over the double covering rigorously right now. We're just gonna take them as they are, okay, as the space of orthogonal transformations with the 1, 3 signature, okay, just being double covered by this general by this special linear group, okay. Now a pure rotation about an angle. Let's take a pure rotation to be the exponential of I theta over 2 times the third Pauli matrix, okay? And this would be about we're choosing this, the z-axis, okay, about the z-axis. And for spinor representation, let's say we want to do a 2 pi rotation, so a of 2 pi. What we'd be left with is 2 pi, so it'd be I minus pi sigma 3, which is cosine pi I minus I sine pi sigma 3, which would give us the negative identity if you were to compute that. Okay? And what this negative identity does is it tells us how the space-time vector is transforming, right? Or it's telling us how this matrix will transform this space-time vector. So if we have x prime and we act on x here, prime, if we take the dagger of it, this should give us, again, if we took the dagger of this would be a plus or a minus I, just because it's the complex transpose. What we'd be left with is negative I x, negative I x, right? And so space-time will return to itself after 360 degrees, okay? So we still are left with this transformation giving that particular transformation, but if we did a complete second rotation, let's say 4 pi, this would give us a of 4 pi, which gives us the positive identity, and the spinor will return back to its original value. So what's interesting is spinors must be rotated by 720 degrees to return identically to itself, which you've probably heard before, but you don't want to, the sign change that's happening is not a quantum mechanical oddity. That's the first thing you need to actually think about. It's actually a direct consequence of the double cover topology of this Lorentz group. So that's really important to emphasize. And the vectors are being built, the spacetime vectors are being built from the bilinears of spinors. So we would have x being built by the bilinear of these two spinors. And these lose the information. They lose that topological information of the fundamental spin structure of space-time. So quantum states, just being single-valued up to a phase, they can be represented by spinors that faithfully carry that extra sign, and that's why relativistic quantum mechanics naturally is going to demand wave functions that themselves are spinors and not vectors. So wave functions become spinors in relativistic quantum mechanics. All right? Now, a standard recipe for building a first-order relativistic wave equation would be if we took a standard quantization recipe and said energy goes to partial derivative of time. The momentum vector just becomes IH bar nabla, and we just kind of substitute this into the relativistic dispersion relation here, where we have PC squared plus m squared c to the fourth, and then you would obtain something called the Klein-Gordon equation by substituting in everything. All right, where the D'Alembertian is defined as 1 over c squared dt squared minus nabla squared. However, Dirac, he wondered if you could take a first order equation whose square still reproduces this Klein-Gordon equation. So Dirac was like, can we make this first order? So what he initially tried to ask was how, if we took the square root of the square of the momentum, this itself is not a polynomial, right? But it can be represented by matrices. And so in kind of that same way, we were thinking, or Dirac was thinking, is there a form D, or a Dirac operator, such that if we had some gamma mu with the differential operator now being indexed over spacetime, and gamma matrices that are indexed over spacetime, such that to ensure that they give us the proper Lorentz invariance under different relativistic frames. The constant matrices here, gamma should return us, really, if we were to square this operator, we would want this D'Alembertian quantity times the identity. And the identity is this space of internal degrees of freedom. Okay? It's in the space. So I is in the space of internal degrees of freedom. Okay? And it's an identity matrix. So fundamentally what we're trying to do is compute gamma mu, gamma nu, del mu, del nu. And what's happening here is, since these partial derivatives, we're going to assume that they commute, only the symmetric part of this, of the gamma matrices are going to contribute to this Dirac operator. So we would postulate a 1/2, basically the commutation relation between these matrices. Okay? And this is going to be equal to the square of the Dirac operator. Now, for this to equal this, what does this need to equal? Or this entire thing, really? We need it to equal the Minkowski metric, right? It better equal the Minkowski metric. With contracted with our mu and nu indices times the identity matrix. So what we're going to do is propose something called the Clifford algebra relation. And what that allows you to do is this is going to encode the Minkowski metric. So we'll take the commutator between gamma mu and gamma nu to be equivalent to just literally that, the commutation. Plus gamma nu, gamma mu. And that needs to equal, it needs to make sure that this quantity gets retrieved, or that we get kind of the identity and the Minkowski metric out of this to ensure that we wind up with a D'Alembertian operator. And so what happens is this commutation is going to be equivalent to 2 times the Minkowski metric times the identity. And that condition, this condition here, the Clifford algebra relation, encodes the Minkowski metric into algebraic multiplication rules for the gamma matrices, right? So this is the smallest faithful representation of the algebra for 4 space-time dimensions that requires these 4x4 matrices, or the Dirac matrices. So with the Clifford algebra, we'll obtain that the square root of the Dirac operator is the gamma matrices times this squared, which gives us the D'Alembert. Thus, the Dirac operator itself is the matrix, square root of the D'Alembert. All right? So now what we can do is write the free Dirac equation. So what the free Dirac equation tells us is that if we have IH bar, gamma mu minus MC, with psi being a Dirac spinor, if we act on the left with a conjugate operator, so if we go H bar nu del nu MC plus MC, IH bar gamma mu del mu plus minus MC. Once we do that, the cross terms are going to cancel out because that's just what they do. And if we use that the square of the Dirac operator is the D'Alembert, then we can find that the negative h bar squared of the D'Alembert is equivalent to MC squared, which implies that h bar squared with a D'Alembert plus m squared c squared acting on psi is equivalent to 0. And the sign, well, where you put the sign depends on your metric convention, but in any case, the component of the spinor satisfies, or every component of the spinor will satisfy the Klein-Gordon equation. And so for a plane wave solution, simply your spinor will look something like some function of u times e to the minus px h bar. And what would happen is if you then square, or that'll immediately give you your mass shell condition. M squared p squared c squared m squared c to the fourth. So you basically, for the Dirac equation, you therefore automatically place the particle on the relativistic mass shell while you remain a first order differential equation in the space-time derivatives. So your spinor nature of psi guarantees that it transforms correctly under the Lorentz transformations. And if you choose to do a Lorentz boost, that's going to mix the components by your spinor representation. But that's going to preserve the covariant form of the equation. All right? So we kind of started with the fact that special relativity is going to provide us this invariant that defines the mass shell hyperboloid, and energy and momentum are components of this Lorentz 4 vector. Okay? Now, the representation theory, the double cover group of, special linear, whatever, this introduces spinors and the fundamental objects that are going to carry that group's topology, and that these vectors are going to be built from spinor bilinears. And then your algebra basically, if you need to write a first order, where is it? Yeah, the algebra. If you need to write a first order wave equation consistent with relativistic dispersion, we have to demand these matrices here that satisfy their commutation to be twice the Minkowski metric. And the Clifford algebra encodes the Minkowski into multiplication rules. And then finally, the dirac operator tells us that it's going to square to the Klein-Gordon operator and ensure that a free relativistic particle, automatically obeys this mass shell condition. So that's why relativity really forces us towards spinors more than we realize. And after having a class in quantum and thinking about representation theory, it makes a lot of sense to motivate relativity from this just straight up quantum field theory idea. So that's kind of the choice that I made for making this the next episode. But yeah, I mean, just the realization of the metric that permits this first order wave equation, right? And again, this is like a plane wave solution, and the equation whose squares physically required, basically it requires the second order one, right? So you have the mass shell, the spin, the relativistic wave propagation. You can see them as just this facets of this geometric and algebraic type of structure itself. Okay? Thank you guys for watching.